Hello everyone, my name is Ned Dimitrov, and today I'll tell you about some new developments in searching for Markovian particles, and this is joint work with Konstantin Karamanis and Dave Morton at the University of Texas at Austin. So let's begin by setting up the problem. Imagine here that we have a graph, and on this graph we have a Markovian particle with an initial position p0, and you know that in general the initial position can be a probability distribution on the states, but in the picture here we've represented it as just this red circle. So the particle moves in a Markovian way, in each position picking a uniformly random neighbor and moving there, as so. And there's a standard way of describing the dynamics here, that the position at time I is equal to the Markov mixing matrix times the position at time I minus 1, where these p's, you're used to them of thinking as them as probability distributions over the set of states. But for the rest of the talk, I want you to think of them as the expected number of particles in each of the states. And you'll see why I ask for that very shortly. So let's change the process dynamics in the following way. Imagine that in each round we're allowed to search a single node. If we happen to search a node where the particle is not, the particle keeps moving. We can search the same node twice in a row if we'd like to. We can jump to an arbitrary other node to search if we want. And if we happen to search the node where the particle is, then the particle stops because we found it. And you can describe the new process dynamics as follows. You take the particle's position at time I minus 1, you multiply it by a search matrix, then by the Markov mixing matrix to get the position at time I. And the search matrix looks like this. It's basically a matrix that has all ones at the diagonal, except for the one row that corresponds to the state that we searched. And on that row, the diagonal has a 0. And what S really represents is that all of the particles that are in the other states, the non-search states, they continue to move through the process as they would, except the particles that are in the state where we searched, those get captured and removed from the process. So that's what the search matrix is doing. And you can see that as soon as we do this multiplication, p no longer sums to 1, and that's why I asked you to think of p as an expected number of particles instead of a probability distribution. So you can generalize this, of course. We can introduce arbitrary detection probabilities. So in the example that I showed you, when we search a node, we find the particle with probability 1. If we find the particle with probability 1/4, then what you would do is in this row, in the diagonal element, you would just put a 3/4 to say that 3/4 of the remaining particles continue moving, and we capture just 1/4 of them. So the basic question to ask for such a process is, where should I search to catch the particle as quickly as I can? And there's at least two ways that you can formalize this. The first is to ask, how do we maximize the probability of catching the particle in t time steps? And the second is, how do we minimize the expected catch time for the particle? And let's just for a moment focus on this first objective, maximizing the probability of catching the particle in t time steps. So if I were to give you this problem, and if you were to think for about 15 minutes, you would soon come up with the following greedy strategy. So in the greedy strategy, what you do is on the ith round, you just search the state that has the maximum number of expected particles in it. So you're just myopically choosing the best search point just for that round. So let's see exactly how badly this greedy strategy does. So here's an example graph. It's set up as a number of levels. The particle will start over here on the left, and we'll have a number of levels that the particle goes through. And at each level, there's 3 nodes. There's this top node and 2 bottom nodes. The particle goes to the top node with probability 1/3 minus epsilon, and to each of the bottom nodes with probability 1/3 plus epsilon over 2. What these cones over here represent is that if the particle makes the transition from this state to this cone over here, what this is really is many, many paths that lead to many, many nodes, all of which are connected to each other uniformly randomly. So basically, once the particle gets over here, it's extraordinarily difficult to find it, because at every time period it mixes completely, and you don't know at all which state that it's in. So let's see what the optimal search strategy for such a graph would be. Well, in the first time period, we could search here, in the second here, in the third here, and so forth, until in time period t, we search this final node, and then we find the particle with probability 1 in t time periods. But let's see how the greedy strategy does. So in the first step, it's going to search one of these two bottom nodes because the particle is here with 1/3 plus epsilon over 2 probability in each of these. So we get about 1/3 of the expected particles. We lose 1/3 of the expected particles. That's the particles that made this transition here. And 1/3 of the remaining particles continue to move through the levels. Those correspond to the node that we didn't search down here. In the second step, a similar thing happens. We get 1/3 of the remaining particles, we lose 1/3, and 1/3 continues moving through the levels. So let's see what the total loss is. In the first round, we lost 1/3 of the particles. In the second round, we lost 1/3 of the remaining third, and so forth. And so you can see when you do the summation, we lose about 1/2 of the total particles in the system. So what we've seen is an example where the greedy policy catches the particle with less than or equal to 1/2 of the probability that the optimal policy catches the particle. But what's surprising, and what we'll see in the rest of this talk, is that for all graphs and all Markov chains on those graphs, the greedy policy always catches the particle with at least 1/2 of the probability that the optimal policy catches the particle. And this is also for all time horizons t. So what this is really showing is that the greedy policy is a half approximation algorithm for the search problem with the maximized probability objective. So before we continue to show that result, let me tell you a little bit about how we got into this problem. So we got into this problem from the point of view of nuclear smuggler capture. So imagine here that we have a map of Russia, and these green dots represent nuclear facilities, and the blue dots represent border crossings. So imagine that some nuclear material was stolen from some facility, say this one, and we know that the smuggler would like to take it out of Russia and into Europe. So the question is, in what town should we search for the smuggler? If you model the smuggler's movement as a Markov chain with a drift from the source to his destination, then the search problem exactly corresponds to which towns we should search for to try to find the smuggler. But really, the search problem is one of the oldest in operations research. It originated in the Anti-Submarine Operations Research Group of the US Navy during World War II. And there have been at least 2 full texts written just on this problem and different variants thereof. So we've already seen that there's at least 2 different ways that you can formalize the objective function, either maximize the probability of finding the particle in t time steps, or minimize the expected catch time. You could also have discrete or continuous search effort. What we're talking about is discrete search effort because in each time period we get to choose a single node to search in, but you could really get a search budget that you get to continuously allocate on all of the states. You could have moving or stationary targets. Your search could be constrained to create a path, so this is like the searcher is a moving person. You could have more theoretical questions like, is this problem hard? Can you approximate it? And there's lots and lots of other variants like continuous space, faults, targets, different kinds of detection functions, etc. But for the purposes of this talk, we're going to just focus on 4 different variants. We're going to consider the 2 objective functions that we mentioned at the beginning, the maximize probability objective and the minimize expected catch time objective. And then we'll talk about discrete effort and continuous search effort towards the end of the talk. And what we're going to do is we're going to, in each one of these 4 boxes, by the end of the talk, place something interesting. So you already know what we're going to place in that first box, that the greedy strategy is a 1/2 approximation to the discrete search effort maximize probability objective problem. So let's see why that is. So here's the picture that we had before. We had a graph with a Markovian particle with initial position p0. But instead of thinking about it like this in terms of a graph with connected nodes, I want you to think of it as a number of glasses, each full of water. So we'll have one glass that corresponds to each one of the nodes of the original network. And the amount of water in the glass corresponds to the expected number of particles in that node. So originally, our process dynamics worked like this. The particle's position at time -1, we multiply it by the search matrix and the Markov mixing matrix to get the position at time I. So let's see how to visualize this in terms of our glasses. When we decide to search node U, let's say that we've decided to search node 3, what happens is we sip all of the water out of that cup, and then the remaining water gets redistributed across the cups as specified by this Markov mixing matrix over here. So to do our proof, or to give you an intuition of the proof, we just have to introduce a tiny bit of notation. We'll use calligraphic letters to designate search policies. And then for a particular search policy in an initial condition P0, we'll have the sip size be equal to the amount of water that's removed in the very first step of the search policy. And we'll have the drink size for a time horizon t be the total amount of water removed by the search policy in t time steps. So let's go back to our initial condition and think about getting a couple of useful lemmas to help us in our proofs. So for the first lemma, let's imagine adding a little bit of extra water to some of the glasses here, with this extra water being denoted as x. Then the claim is that adding this water doesn't hurt. In other words, the search policy gets at least as much drink size with the extra water as it does without it. And the reason for this is as follows. If you think of the water that was originally there, the non-x water over here, it moves throughout the system in exactly the same way as it would whether the extra water is there or not. And so if we capture it in this situation, then we're going to capture it in this situation. So the only thing that might happen is we might drink a little bit of extra water because of this x that we added initially, and that gives us the lemma. So let's go back to the initial condition, and this time think about removing a little bit of water, denoted by r. So the claim here is that as long as we give ourselves credit for all this water that we removed initially, then this doesn't hurt us. So why is this? Again, the water that is blue here is going to keep moving through the system in exactly the same way as it did before, regardless of whether this water R is here or not. So if we drink this blue water over here, then we're going to drink it over here as well. The only thing that might happen is we might miss on drinking this water R that we removed, but we've given ourselves credit for all of that water ahead of time. So that gives the second lemma. And I'd like to point out that I'm purposefully being sloppy with notation here. For example, is R a vector or a scalar? You can definitely formalize this as much as you want, but the purposes of today's talk is just to give you the basic intuition. And another point I'd like to make is that for both of these lemmas, we're crucially using the Markov properties. So what we needed is that the water to move throughout the system exactly in the same way, whether this water R is here or it's not, and the same thing for the x, whether the x is there or it's not. So for example, if the transition probabilities were dependent on the expected number of particles in a state, then these lemmas would not be true necessarily. So let's go over this slide piece by piece to see how we get the result. So we have the two lemmas that can help us, the add a little bit of water lemma and the remove a little bit of water lemma. So we'll let O star be the optimal policy and G be the greedy policy. So here we'll start with the drink size of the optimal policy from an initial condition P0. And for the very first step, what we're going to do is apply a remove a little bit of water lemma. So here we've removed a little bit of water, but we've given ourselves credit for that ahead of time. In the next time period, or in the next step, what we're going to do is we're just going to roll this drink size out by one time period. So the drink size at a time horizon t is equal to the sip size, what the policy gets in the first round, plus the drink size in the remaining t minus 1 rounds, where we've changed the initial condition to account for the fact that we've had a bit of a drink in the first time period. So for the next step, what we're going to do is we're going to use our add a little bit of water lemma. And the amount of water that we're going to add is exactly this term that we drank in the first time step. So that gives us the step from this line to this line. And now let's look at the two terms that came out up front here. So this is the sip size of the greedy policy from an initial condition P0. This is the sip size of the optimal policy from an initial condition that has slightly less water than P0. But we know that the greedy policy always drinks from the class that is most full. So in other words, this term has to be smaller than this term. So that gives us the next step where we can bound these two terms by 2 times the sip size of the greedy policy. And now if you look at this, what we've done is rolled everything out forward by one time period. And we got 2 times the sip size of the greedy policy out here. So you can use induction to roll this out the rest of the way and get 2 times the drink size of the greedy policy. And this gives us the result that the greedy policy always gets at least half, the particle with at least half of the probability of the optimal policy. But actually, if you go back and are very careful about formalizing that proof, you'll see that the proof shows a lot more. So first of all, it works for any detection probability. It doesn't have to be a detection probability of 1. Second of all, it works for a more general problem called the set search problem. So in the set search problem, what we're given is the original graph, but we're given a bunch of subsets of the original graph. So here's a subset of the nodes, another subset, another subset. And in each time period, we're allowed to choose one of these 3 sets which to search. So you can see the original problem we described is just a special case of this where we were given all the singleton sets to search. So it works for the set search problem. It also works that if the Markov transition matrix is changing from time period to time period, in other words, if the transitions are a non-time homogeneous Markov chain. And finally, another result that you get out of it is that you can look at the proof from a resource augmentation point of view. Let's give the greedy algorithm a slightly better detection probability than the optimal algorithm. So the ratio of the detection probabilities here will be f for f less than 1. Then it turns out that the greedy policy is a 1 over 1 plus f approximation instead of a 1/2 approximation. So you can see if these are equal, f is 1, and we get the 1/2 approximation result that we've been talking about. But what this really says is that if you're better at finding the particle once you actually get to a state, then you don't have to be quite as careful about which state to search. The greedy policy, when it has a better detection probability, becomes a much better approximation to the optimal policy. Okay, we have this 1/2 approximation result for the greedy policy discrete search objective. But the question is this problem hard? Is it even interesting that we have a 1/2 approximation result? So let's see why that is. It's already known that some search problems are hard. So for example, if you have a searcher that's constrained to make a path throughout the graph, then it's been shown that that's hard, but not for the problem that we're talking about. So we're going to show that it is hard, and we're going to do so through a reduction from the standard 3-sat problem. So just for reminding everyone, the 3-sat problem is as follows. Somebody has given us a Boolean formula that consists of a bunch of clauses, and each clause has 3 variables in it like this. And the question is there a satisfying assignment to this Boolean formula? So this problem is NP-hard, and we'll show how you can solve this problem given a black box for solving the set search problem. So the first thing that we have to do is I have to tell you how to start with a 3-sat problem and construct from it a set search problem. So we'll do this as follows. We're going to create a graph that consists of a number of layers and a number of columns. So we're going to have one column for each one of the clauses in the original Boolean satisfiability formula. And we're going to have one row for each one of the variables in the formula. And then at each intersection of row and column, we'll put 3 nodes, a 0 node, a 1 node, and a star node. And in addition, we'll have these small nodes over here that are the start nodes for each of the clauses. So then I have to tell you how the transition probabilities work, and they're going to work as follows. If a variable appears non-negated in the clause, then we'll connect it on that layer with the node that's equal to 1. If a variable appears negated, then we'll connect it to the node that's labeled 0. If a variable doesn't appear, then we'll connect it to the star node. And similar for x4 here, it appears non-negated, so we connect it to x1. And the same thing's happening over here. The first one appears negated, the second one doesn't appear, the third one's non-negated, and the final one is negated. And so now I have to tell you which sets you're allowed to search to completely specify the set search problem. So in each time period, you'll be allowed to search one of 2 sets, either all of the 0 nodes or all of the 1 nodes. And it's not hard to show that there's a 1-to-1 correspondence between assignments, satisfiable assignments to the original search formula, and search plans that capture the particle with probability 1 by the final round down here. So, for example, if we search the 0 set in round 1, then that means that we're basically assigning a 0 to x1. If we search the 1 set in round 2, then that's like assigning a 1 to x2. And this correspondence gives you the reduction. So we've shown that the discrete search maximized probability objective is hard, and we have an approximation algorithm for it. So let's move on to the other objective function that we talked about, minimizing the expected catch time. What can we say about that? Wilson showed that if you can solve the probability objective problem, then you can solve the expectation objective problem as well. Well, we've just shown that you can't solve the probability objective problem, but we do have an approximation algorithm for it. So does that mean that you can approximate the expectation objective problem as well? And it turns out that this problem is hopelessly hard. In fact, we're going to show a super hard inapproximability result for this problem. So just to show you exactly what we're going to show is we show that for any constant delta less than 1, it's NP hard to approximate the expectation objective discrete search problem within a factor of n to the delta, where n is the description size of the search problem. So just to give you a quick explanation of what this means, it's NP hard to approximate within n to the delta for any delta less than 1. But if delta is equal to 1, then it's trivial to approximate. You can get a linear factor approximation scheme just by returning a constant, because you can find the particle just by searching a uniformly random state in each time period. So let's see how we're going to get this result. So for the construction, what we're going to do is take our construction from the previous problem, and just at the end we're going to add here a very large number of nodes connected to the final node in each column. So this is B nodes for a very large B, and each of these nodes are connected to each other uniformly randomly. So let's see how the proof works. So let's say that there are V variables and C clauses. So imagine that we can catch the particle with probability 1 in the first V time steps. So that's right down here, as the particle is moving from the start nodes to the final here. Then the expected catch time must be less than V. That's because we captured the particle with probability 1 over here. Otherwise, at least with probability 1 over C, one of these columns is going to get down here. And then once the particle is down here, it's going to take us B time steps to capture it. So if we don't capture the particle with probability 1 in the first V time steps, then the expectation is at least B over C. So if we let B be some very large amount, so the number of variables times the number of clauses to some power m for some integer m, then this makes our total description size be about Vc to the m. So if somebody gives us a Vc to the m minus 1 approximation algorithm, then we can distinguish V from B over C. We can distinguish V from V times C to the m minus 1. And this is because this is exactly the approximation factor that we're assuming that we have. So you can see that Vc to the m minus 1 corresponds to n to the m minus 1 over m. And since m can be arbitrarily large, we can basically show that you can't have an approximation factor for any constant delta less than 1. So that completes this box. And for the other two boxes, we have the following results. You can solve the continuous search effort maximize probability objective via convex optimization and polynomial time. And you can approximate the minimum expected catch time objective in continuous search effort problem. You can get an epsilon optimal solution in polynomial time using this box as a building block. Thank you very much for listening.